Good morning, my dear friends. So coming to the next topic, so here I am going to tell you about what you mean by boundary condition and what are the different types of boundary conditions. Okay, and different numerical different method problem we are going to apply the different boundary condition. Okay, so and one more derivation we are going to study here is the temperature effect. Okay, so what is the temperature effect in the FEM? Okay, so let me understand first the boundary condition and what are the different types of boundary condition we are going to apply. Okay, so based on boundary condition only we are going to get the final result. Okay, stress, strain, displacement, reaction, all those things. Okay, so let me understand boundary condition here. So boundary condition is nothing but what? It is a kinematic constraint applied to a body. Okay, so it is a constraint. Okay, kinematic constraint applied to a body or a given problem to the constraint the rigid body motion. Okay, it's going to fix, that is a okay, suppose for example if you consider a bar. Okay, so here in the bar one end is fixed, another end free, means one end is fixed point is called as a where the boundary conditions are at node point number 1 is fixed, means where u1 f1 going to consider as 0, that is called as a boundary condition. Okay, so hence the boundary condition in terms of the fixed degree of freedom will be considered. Okay, or it is a known values of the basic variable are applied. Okay, some basic variable we are going to apply at the different node or the boundary layer. Okay, so after applying the boundary condition we are going to get the final result. Okay, that is what the boundary condition. Okay, so here one more I will repeat, the boundary condition is the kinematic constraint or applied to the body to the constraint to the rigid body motion. Okay, hence the body condition, then the boundary condition in terms of the fixed degree of freedom going to consider. Okay, so it is shortly called as what? BC. Okay, that is the capital B and C, that is boundary condition. Okay, there are different types of boundary conditions are there depending upon the how you are going to use the problem. Okay, how you are going to what use the problem in a finite element method. Okay, so here there are five, for your syllabus there are 5 different types of boundary condition going to apply. Okay, so that is what the homogeneous boundary condition and non-homogeneous boundary condition, like that we have to study. Okay, so in the homogeneous boundary condition, in this boundary condition what the variable at the boundaries, okay, that is the extreme layer, okay, of the problem are often going to consider as 0, or it should be known value, either it is a 0 or known value. Okay, suppose if it is fixed means 0, otherwise they will mention. Okay, such in this condition, that is called as homogeneous boundary condition. Okay, so non-homogeneous boundary condition means what? So in this boundary condition the finite non-zero values of the variables are going to specified at the particular node or boundaries. Okay, that is the difference between homogeneous and non-homogeneous. Okay, here we are going to consider the known zero, or the we should know the values, otherwise here in this non-zero values of the variable are going to specified at the particular boundaries is called as non-homogeneous boundary condition. Okay, if you solve on numerical problems on homogeneous boundary condition, non-homogeneous boundary condition means you will understand this. Okay, so now coming to the third one. Okay, so that is the third one boundary conditions are for the heat transfer problem. Okay, so let us assume that this is a heat transfer problem. Okay, so here it is a surface, okay, upon which there are 2-3 forces of the forces are acting on, that is S1, S2, S3. Okay, this is called as a boundary condition. Okay, so S1 stands for what? Boundary on which the value of the temperature is going to specify. Okay, for reference if you consider the temperature problem, that is a heat transfer, means we have to consider the temperature and the heat flux and the convection, how the heat going to losses. Okay, these are the 3 boundary conditions we are going to apply in the heat transfer problem. That is what? S1 is equal to boundary on which the value of the temperature is going to be specified or should be applied. S2 is nothing but what? Boundary on which the heat flux Q is specified, and S3 is equal to boundary on which the convection heat loss is specified. Okay, so these are the S1, S2, S3 are the boundary condition for using in heat transfer problem. Okay, you have to remember 1, 2, 3. Okay, similarly for the boundary condition for structural problem. Okay, so this is the problem, this is a surface. Okay, so upon which there are 2 forces are acting, these 2 are called as boundary condition for structural problem. Okay, where S1 is equal to what? Boundary on which the value of the displacement is going to 0, that is suppose if it is fixed, means you are going to consider as u is equal to 0, that is the displacement is equal to 0, and boundary on which the value of the displacement specified. Okay, u is equal to constant, that is S2 is equal to, sometimes they may give constant values. Okay, these are the 2 boundary condition for structural problem. Okay, whereas in the heat transfer problem there are 3, one is temperature, one is heat flux, one is how the heat going to losses. Okay, these are the boundary condition for heat transfer problem, whereas here structural problem, here the displacement that is fixed or we are going to consider as a constant value. Okay, these are the 2 boundary condition for structural problem. Okay, coming to the boundary condition for fluid flow problems. Okay, the fluid flow, what is the difference between the temperature problem, that is the heat transfer problem, and fluid flow problems, where we are going to consider the heat. Okay, that is the temperature, but whereas in the here fluid flow problems we are going to consider the fluid. Okay, so here again there will be 2 forces will be there. Okay, by it is 3 but actually 4, that is a 2. Okay, so S1 stands for boundary on which the parameter is constant, that is velocity of the wall is 0, and boundary is equal to on which the gradient of the parameter is constant. Okay, S3 is not there, by mistake it is there, only the S1 and S2 for fluid flow problem. Okay, now coming to the Next, these are the 5 different types of boundary conditions. Okay, so here the fluid flow, thermal flow, heat transfer, structural problem, homogeneous, non-homogeneous boundary condition we understand. Okay, so next, coming to the second part, that is the temperature difference. Okay, this is most important. Okay, so what is the meaning of temperature effect? Okay, so here, okay, so we will derive on this equation. Okay, derivation is there. This is very simple, but it may ask to 4 to 5 marks. Okay, so temperature effect. Okay, so what do you mean by temperature effect? Okay, normally what do you mean by temperature? Means it is a depending upon the environment or depending upon the given problem, it will variation takes place from one stage to another stage. Okay, that is the temperature difference. Okay, so here it is normally temperature difference we are going to denote as delta T. Okay, so let us assume take a one bar. Okay, when the free expansion is prevented in a member, consider any member. If the free expansion is prevented, the change in temperature causes stress in the member. Okay, if just you extend means there is a lot of changes happen in the temperature happens in the particular member. Okay, so when the distribution of a change in the temperature T is known, the strain due to this change in the temperature can be considered as the initial temperature, the initial strain as epsilon naught. Okay, so if you apply temperature, because of that there is a strain will be changes. Okay, that strain, initial strain, going to consider as strain, that is this symbol, that is epsilon naught. Okay, so T is the temperature, epsilon, that is a change in initial strain. Okay, for one dimensional problem, the thermal stress is given by sigma is equal to capital E is material property du by dx, that is a change. Okay, minus E into alpha delta T. Okay, where alpha is equal to what? Coefficient of thermal expansion, and T is what? Change in temperature, that is delta T is equal to change in temperature. Give equation number 1. So this is a total, this is a change in difference, minus this is the initial value. Okay, for 2D problem, so for the plane stress problem, the initial strain epsilon naught can be given by epsilon naught is equal to change in temperature. Okay, so that is alpha delta T 1 for the first material, alpha delta 2 for the second, and 0. Okay, so 2D means x and y direction, z will be 0. Okay, delta T1, delta T2. Okay, alpha delta T1, T2. Okay, epsilon naught. This is for 2D element. Again, similarly for the strain element is equal to what? Here the initial strain going to consider here 1 minus gamma. Okay, epsilon naught is equal to 1 minus gamma alpha delta T into 0. Okay, where this gamma is equal to what? Poisson ratio, that is a constant value you are going to feed in the ANSYS software. Okay, so okay, the finally the stress strain related by these two equations. Okay, consider equation number 1, 2, 3. Okay, the stress is equal to what? The stress component we are going to write as, this is very important. Okay, final answer is very important. Okay, stress is equal to D, that is a material property. Okay, epsilon naught, that is what? Strain minus initial strain. Okay, this is epsilon naught. Okay, so again we can write this, if the modified equation is equal to stress is equal to D capital B, B nothing but the strain displacement matrix. Okay, U minus epsilon naught. Okay, this is the final equation for the temperature effect. Okay, so this equation you have to remember. Okay, they may ask you 4 to 6 marks. Okay, write a note on temperature effect. Okay, so here where capital D stands for what? Material property of the matrix, and B is equal to strain displacement matrix, and U is the displacement factor. Okay, you have to remember these. Okay, I will repeat here again. Temperature effect, consider any member. Okay, any n member. Okay, that going to give in under free expansion, there is a lot of change in the temperature. Okay, because of the change in temperature, a strain will be produced in that component. Okay, so for again, if you consider 1D element, 2D element is different. Okay, for the thermal stress 1D case means stress is equal to, that is E is equal to what? Du by dx, that is the change in temperature. Okay, for initial order. Okay, minus of E alpha delta T, this is the beginning, this is the after, once we expand the takes place. Okay, so this we have to remember. Give equation number 1. Okay, so where the coefficient of thermal expansion in the case okay, in the where this alpha is nothing but what? The coefficient of thermal expansion, and T is the change in temperature of the difference. Okay, so this gives equation number 1. This is in the case of one dimensional element. Okay, so you have to remember only stress is equal to E in material property du by dx minus E alpha delta T. Okay, similarly for if you consider 2D case means change in strain. Okay, change in strain for the plane stress problem and the plane strain problem. Okay, so this is for the in the plane strain problem, z direction strain going to consider as 0. Okay, so here alpha delta T for the first x, or alpha delta to the second, and 0. This is x, it is in the x direction, this is in the y direction, z direction is 0. Okay, similarly for the plane strain problem, here 1 minus gamma. Okay, that gamma indicate what? The Poisson ratio, alpha delta T1 or alpha delta T2, z direction is component is 0. Okay, give option number 1 for this, give option number 2, and give option number 3. Okay, the stress strain relationship for by using 1.56 and 1.57 equation, we are going to write like this. Okay, stress is equal to d epsilon naught minus change in strain. Okay, this can be modified as stress is equal to d b u minus epsilon naught. Okay, where d stands for what? Material property of the matrix, and the strain displacement matrix, that is called as the capital B, and is a displacement vector, u is a displacement vector. Okay, so this is very important. So temperature effect. Okay, but from this ppt you are going to you just to understand that how you are going to apply the boundary condition. Okay, boundary condition means what, and what are the different types of boundary condition. Okay, for the boundary condition in the case of this heat transfer problem 3, and the structural problem 2, and fluid flow problem also only 2. Okay, you have to remember this boundary condition. Okay, boundary conditions are the kinematic constraint applied to the body to the constraint to the rigid motion is called as boundary condition. Okay, so I hope you understand this boundary conditions, all those things. Okay, so what are the different types of boundary condition? Okay, homogeneous and non-homogeneous. In the homogeneous boundary condition, what here the boundaries often are 0 or going to consider as constant value, or here in the non-homogeneous we are going to specify the some boundary condition. Okay, that is homogeneous and non-homogeneous. Okay, so here we are going to solve the numerical problems. Okay, boundary condition. Okay, I already explained in the basic steps also. After once if you apply only, then only you can able to calculate the stress strain. Okay, once if you apply the boundary condition means, then you are going to calculate what stress strain or displacement reaction, that given answer. Okay, without boundary condition you cannot apply, you cannot solve the numerical problems in the finite element process, in the finite element subject. Okay, so I hope you understand this slide, what is the temperature effect and what are the different types of boundary conditions which are going to use in the problem. Okay, so thank you.